Thank you for being here. This is an invited talk in the Gaming the Data invited talk series. This series has been made possible by generous support from Cisco, EMC Informatica, SAS, the EAP Partners Program, and the NC State Engineering Foundation. The invited speaker that we're going to listen to today is a distinguished person. You can see the credentials here. He has very modestly has asked me to say that he's actually joining Penn State in January 2014. And this is going to be the Department of Geography and Institute for Cyber Science, but he's one of ours. By training, he's a computer science person. And so his interest is, he will tell you about his research interests. And I'm giving the floor to you. Welcome, Guido.
Thank you. Make me earn it. So thank you, Dr. Cherkova, and it's really an honor to be here. I want to thank you for inviting me. I'm super excited about being able to tell you a little bit about my research. And this is a very exciting time for geoinformatics. Never in the history of our planet we have known so much. We never had such easy access to data. We can find out in near real time virtually everything we want to know that is occurring anywhere on the planet right now. And never in history our society has been so much at risk. And this is in part because of environmental hazards. They pose a constant threat on the sustainment and survival of our civilization. Nowadays, a single event can claim damages for billions of dollars, can cause thousands of lives, and can destroy the environment. And this is because of the proliferation of megacities, nuclear power plants, nuclear storage facilities, and all other facilities whose destruction pose an unacceptable risk. The kind of hazards that we're dealing with are natural, man-made, or also technological. This is something new that we start talking about right now. We really talk about the massive collapse of infrastructure that we need for our survival to function properly. Things like grid lines, communication networks, and so on. And at the very same time, we are observing an exhaustion of resources. And we have to go to places that are geographically or geopolitically more difficult to reach, and this may cause a new threat on the planet, on the environment. The reason why we know so much about the planet is because of remote sensing observations, that they give high-resolution data constantly, every day, about every part of the planet. And then we have numerical models that take those observations and they can tell us what is likely to happen in the future, but they can also help us explain what happened in the past. And also, this is something really new, last few years, we have social media. So we have a ground view that tells us a tremendous amount of information, not exactly about what is happening, but how people perceive of what is happening. And we can use this data to fill the gaps in our observation. And then we have geoinformatics, a set of tools that we use in order to analyze this big data, this massive amount of data. And the reason why we need advanced tools is right here. The rate at which geospatial data are generated exceeds our ability to analyze them. So we really need sophisticated algorithms to cope with this massive amount of data. Those are my passions, and environmental hazards is the main theme of my research. Remote sensing, numerical data, and social media are the main data sources for my research. And geoinformatics are the algorithms, are the main framework that I use for my research. Now, geoinformatics is truly interdisciplinary, and I wanted to give you a sense of truly how we have to reach across different disciplines to put things together. And I thought, maybe I will just show you who are the people I collaborate with, to get a sense. Even though I'm a computer scientist, my training is in computer science. I'm in the Department of Geography. So not surprising, I keep quite a number of collaboration with geographers. But then, as I said, I'm a computer scientist, so I collaborate very actively with CS people. And a lot of my research has to do with atmospheric science. Remote sensing, as we have already seen it. Civil engineers, especially to describe the damages that are occurring because of hazards. And electrical engineering. And here we have Dr. Krim, one of yours, coming from the best electrical engineering department in the country. Environmental science, and very new, this is the new things, the social media, the social scientists. So you see, this is pretty much a collection of the people I work with. The thickness of the link is a function of how many papers, of how many students we have worked on together, or what is, the perceived day-to-day interaction. And when I showed it to my wife, just 2 days ago, she said, "Oh, you really like to be at the center of attention." That was not exactly the intent. So let's start with data mining. This is really the central core of my research. And nowadays we live in, you probably recognize this image. We live in a world that is rich in data, but is pure in knowledge. And really what we're trying to do, to go from data to knowledge. And here the problem is that the raw data per se, it's useless. It's just a collection of symbols. It's recorded information. What we need is the knowledge, are the patterns in the data, very important, that we use to solve a problem. Okay? And further important is the fact that we have to do so automatically. The data is too large to do that by hand. It's okay to prototype it manually, but then when we want to deploy a system, it truly has to be fully automatic. And already talked about geoinformatics, so this collection of tools that we use to learn patterns from this massive amount of data. And geoinformatics itself, it's a new discipline, but it's really borrowing from existing technologies. Methods originate from machine learning and artificial intelligence, which is really my background. But then we also have GIS, graphical information system, statistics, mathematics, research on databases, and of course there are many others. You will see throughout my slides that at the bottom there is footnotes. Those are what I consider relevant publications. I'm a little bit egocentric here, so all those are my publications. This is a recent book. It just came out about 2 months ago called Data Mining for Geoinformatics, in which we explore some of those topics that I'm describing to you. So, learning data from knowledge, we already talked is important to learn. And what we have to remember that learning is a goal-oriented task. We don't learn just for the sake of learning. We learn because we want to solve a problem. And because we are trying to solve a problem, it means we know something about this problem at hand. So we are not trying to go from data to knowledge. We're trying to go from data plus something that we already know about this problem to new knowledge. And here it's very complicated because sometimes this background knowledge comes in forms that are not very human-friendly. You may talk to a domain expert and you say, why is this solution is right? And he says, oh, it just looks right. The truth is that sometimes analysts, they develop a sensitivity to a problem just by looking at it over and over and over. And they cannot really explain why something is good. They just feel that it's good. And this is very hard. And then when we talk about learning, what does it mean to learn? Of course, we are learning content. So, and this is not the basic form of learning. But then organization is very important. Sometimes to solve a problem, we don't have to get new data. We just have to learn how to properly reorganize the data that we already have. And, we have talked about this a lot with Radha. This is her research. And this is extremely, extremely important in a lot of those geoinformatics problems. And sometimes the certainty of the data. We really want to learn whether or not we can trust something. It's, some observations that we made last month, they may no longer be true today. So we might learn to see whether or not this data still holds value nowadays. And then spatial and temporal constraints. All the problems related to the Earth, they really have spatial and temporal component. And we have to have algorithms that can cope with those. And then, of course, we scale it up. We have things like big data and big simulation. So we have data that is massive in size, yes, spatial and temporal dimensions, may incomplete, irrelevant data, may rapidly changing, like Twitter streams. We cannot just say Twitter, oh, please don't send me more data, or tell people not to tweet. The data will keep coming and coming, and we have to learn to cope with that. Data may be highly heterogeneous. We may want to compare remote sensing data with model data. And the central core of a lot of those problems is the data fusion. How do we put everything together? Of course, we use supercomputers. I'm very fortunate. I have access to Yellowstone, NCAR Yellowstone. It's currently in Wyoming. It's one of the fastest supercomputers for research use in the US. But sometimes even a single supercomputer is not enough. We have things like XCity. This is a consortium of universities, research centers that have access to high-performance computing, and it's possible, to share the data. So some of the centers, they specialize in storing data, whereas some centers specialize in raw power. And it's possible to, to basically take leverage of the best systems. And here we have not only NCAR, Yellowstone, but also Penn State. So we're part of this system. And big data is indeed a very big deal. This is a press release from the Oval Office from our president. This is from last year. It describes why big data problems are important for our nation's future. And it describes different agencies that, they provide big data research funding. Of course, after this announcement, I was very hoping for the big money announcement. It didn't come up. But there is plenty of opportunities that are, for big data problems. This press release doesn't talk about geoinformatics per se. Probably our president doesn't know about it, but this is being recorded, so Mr. President, geoinformatics is very important. I live close to the White House. Let me know. I'll come to tell you all about it. And here comes my contribution. When I was invited to give this talk, I prepared some slides. I put some of the slides I put together, and I came up with 183 slides. And I figured out that's too much. If I tell them everything today, then they will never invite me again. So I have to be selective. And in my usual visual way, I took every article I published in the last 10 years, pretty much. It's a dot on this graph. On the horizontal axis, I have applications, theoretical work, earth science problem, hazards, and energy problems. On the vertical axis, I have types of data that I used. Synthetic data, NAM is numerical atmospheric models, remote sensing data, and social media. So look at this graph, and I was like, oh my God, I'm all over the place, right? But the truth is that, as we said, in geoinformatics, problems have a spatial and a temporal component. So let's see what happens here when I start adding time. And of course, the time for us in academia really goes in discrete intervals. This is the work that I've done for my master thesis. And, Circle is all the work for which I was first authored. In my master thesis, it was Master of Computer Science, I was really doing theoretical work over computer-generated data. And then, I went ahead, decided, to get a PhD in computational science and informatics. I really view it as an applied computer science degree. And I started doing spatiotemporal data mining. And what more perfect than to study remote sensing data that changes both in space and time. And in particular, I've started doing it for hazards. And then, become an assistant professor, and here things become fun. I started having my own students. So, the double circles are the students that I supervise. And of course, during the tenure track period, we are supposed, to expand, our PhD work. So I started taking this remote sensing data, and I applied it both to earth science problem. But then I added an entire new category, numerical atmospheric models. Why atmosphere? Well, because I was interested in remote sensing, and when you look at the Earth using a satellite, you're either looking at the atmosphere or you're looking through it. So I had to do so much studies of the atmosphere that I become competent, and I decided to let's look at some of the atmospheric model per se. And then things became fun. I got my tenure, and here when you get tenure, you can get to work on all the problems that you couldn't work. Well, let's say you couldn't work during your probatory period, so you can see I kind of expanded my horizon, right? And my newest work, so this is about the last year and a half, I start combining remote sensing data with social media, and then something completely new. What I started this summer, I started working on alternative energy. This is the same thing with bubble graphs. The size of the bubble is pretty much proportional to what is my perceived effort into the program. And you can see there is quite a lot of overlap here in the hazards. And then, I have those two lonely bubbles. This is the energy. This is the really new work. This is what I started a couple of months ago, 4 months ago. And then I have my theoretical work. But I then realized that this theoretical work is not really by itself. Every part of the work I've been doing really traces back its origin to what I did for my master thesis. So, it looks almost like a marine animal, right, that has tentacles into all that I've done. Today's talk is about source term estimation of toxic contaminant, which is down here. This is the primary contribution during my tenure track period. And then I want to talk to you about fusing remote sensing, numerical models, and social media during emergencies. That's the big bubble up here. This is the new stuff that I've been doing for the last couple of years. So let's start. Geoinformatics for source detection. This is a typical scenario. There is an unknown source. And some sensors, maybe on a satellite, on an airplane, or on the ground, detect a concentration of potentially toxic gas. What we need to do, we need to find out as quickly as possible where the source was, location, how big it was it an accident or not, was it an explosion or a small leak, was it stationary or was it moving, single source, and there are many different characteristics that we can consider. And to solve this problem, I use an iterative approach. We generate some candidate sources, either at random or using by prior knowledge, some background knowledge. And then for each one of those solutions, we run a transport and dispersion simulations. And then we evaluate them. We evaluate what we have observed from sensors and what we simulated. And then, we loop until, the error is small. And here we got the first scientific problem. How do you evaluate something that has been observed with something that has been simulated? There are several articles in the field. So what I did with my co-author, Dr. Franzese, we took a list of 8 functions which are normally used, and we tested them on some problems. And, we try to see, does it matter? Are they all the same? Are they all different? Are there some functions that are better than others in certain circumstances? And that was exactly what we found out. And we were happy because it means, that there was room for our research. So once we found out that it worked on some synthetic data, we decided, to scale it up. Let's use real data, real observation from the world. This is an experiment done by the US Army in the late 50s. Some sulfur dioxide was released in a field, and then it was measured at concentric circles at 50, 100, 200, 400, and 800 meters from the source. So everything was released here in the center. And different types of atmosphere were sampled, which means different wind speed during the day, during the night, high wind, low wind, and so on. And this one is what I did. I interpolated the values of all the sensors for all 68 releases, and the red line shows the main wind direction that was recorded. Because together with the samples of the concentration, the military also recorded the main wind direction, the temperature, the pressure, and so on, the main atmospheric parameters that govern the experiment. And here we get into the first problem. You see, this one is on the black line is the synthetic, what we have reconstructed using a model and using the atmospheric parameters that were recorded at the field. The dotted line, red dotted line, that is the observations. And each panel is a different line of sensors. Remember those concentric sensors, so 50 meters, 100 meters, and so on. And it worked very well. If you can see the 2 time series almost match perfectly. And here we have the reconstructed synthetic and observed here on those panels on the left. And overall, it works very well. This is a logarithmic scale, so even though it looks a little bit bigger, actually, that's just the tail or the distribution. So it's actually really good. And then we tried another case. In this case, it actually didn't work. As you can see, the error is very large, even though the reconstructed sources are very similar. And the problem was that in 1958, when the experiment was made, the wind direction was not recorded properly. So there is an error about 6 to 7 degrees in the observation. Now it's a problem because, if we just put it in our algorithm as we defined it earlier, then, the error is very large for solutions that are very close. So what can we do? Well, we can use a function that disregards, the wind direction. So a function that compares only overall distribution, like this FB means fractional bias. However, in our first paper, we've proven this leads to poor performance. So another solution is, let's make it an unknown. Let's assume that we do not know the wind direction. Let's let the algorithm discover it. And in order to do so, we need to use something a little bit more sophisticated than the Monte Carlo algorithm we used before. So we implemented the genetic algorithms. I think probably you all know very well what they are. But I always like to cite Darwin, 1859, the main idea behind, those algorithms that they mimic evolution to solve problems. And what is important here that I want you to remember that those algorithms, they perform a stochastic parallel search, and the mutation and recombination are pseudo-random operators. And it works beautifully. So here are the, on the left panels, we have, on the left panels, we have the observed concentrations, and on the right is what we have simulated. So you can see, we were able to find the wind direction very well, and, also the concentration matched, except for this case. This was an anomaly. And if you inspected, what happened is that at the time of the experiments, the wind was very variable. It almost looks like there are three main directions. So the wind first came from a direction, then from another one, then from another one. So when we try to minimize, this is the function that, or the wind direction that minimizes the error. But, other than that case, it worked very well. It worked extremely well for those type of atmosphere. This is much harder because the footprint is smaller. So we have a smaller number of sensors, to compute our errors. So here we get into the problem of the background knowledge. You see, if we don't know the wind direction, then that's fine. We let the algorithm discover it. If we know it precisely, we use it. But what about if we know it, but we're not sure about it? It would be very nice to be able to tell the algorithm, look, the wind is coming from that direction. I don't know exactly with precision the angle, but more or less it's from that direction. And to solve this, we thought about using dynamic type warping. This is a computer science technique very much used, in time series analysis, in which we allow the time axis, so the horizontal axis, to vary. We don't assume that it's fixed. So here on the left, we have, those two functions that I showed you before, where there is, a wind angle. And if we do a one-to-one mapping, you can see, the error is very large. However, if we allow the axis to warp, then, we can, as long as they are isomorphically similar, then, we can perform a search and do a better match. And this can be solved using dynamic programming, so it's extremely fast. And basically, we're doing a search in a two-dimensional space with constraints. And we went ahead, and those are sensitivity analysis on wind angle for the same two cases that I showed you before. The blue line and the red dotted line are just two of the normal functions that are being used. And you can see here that as I change the wind angle from what was recorded at the experiment, the vertical axis, which is the error, shows that it increases dramatically. So just a few angles of error in wind speed, and then our algorithm fails. Whereas with dynamic type warping, which is the black solid line, we were able to achieve the minimum error over a wide spread of angles, almost 20 degrees. So this means that it's enough to know the direction within 20 degrees, and our algorithm would work well. And this is the other case, the one, where you can see that there was an error in observing the wind angle. We're off by almost 10 degrees. And again, the dynamic type warping worked very well. So we're very happy because now, we solve a lot of problems and we can reconstruct our sources. However, those algorithms, they required hundreds of thousands of evaluations. So they're very slow. And each one of those function evaluations is really a big simulation problem. It may take minutes to hours for a single one. And here we have to do hundreds of thousands. And even having access to a massively parallel supercomputer, the solution may be too costly to compute for large problems. Here we're dealing with a small problem. We cannot really scale it up, to a regional scale, something like Chernobyl, for example. So one of the challenges is it possible to reduce those function evaluations? We still want to use this iterative approach, kind of evolutionary algorithm approach, but we really want to reduce the number of evaluations. And we came up with an algorithm that we call this non-Darwinian evolution. And in this evolution, we use machine learning classification to guide the search process. So this is the flowchart. If you take a look at the right side of the flowchart, this is a traditional Darwinian operators. We start with a population, we select the parents, we do mutational recombination, we evaluate them, and then we select the weakest die and the strongest leaf, where everything is guided by those pseudo-random changes. If we take the left side, we have the machine learning classification. At every step, we took an entire population and we split it into the high-performing and the low-performing, so the good one and the bad one. And then we run a machine learning classifier to try to identify what are the causes or the areas of the space, the attribute value relations that cause certain solutions to be better. And we try to generate new individuals only in this sub-region of the space. Again, let's look how this works with a visual illustration. This is a four-dimensional source dimension problem. There are 4 dimensions on each one of those graphs. So we have 2 dimensions on the vertical axis and 2 dimensions on the horizontal axis. I discretized it so that, we can show it. And the solution is right here, where x1, which is longitude, is equals to 3. It's a little bit small to see, but there is a number 3 here. Where x2, that is latitude, is also equals to 3. When x3, which is the size, is equals to 3. When x4, which is the wind direction, is also equals to 3. So this is what I'm trying to look for. A little bit, like 4-dimensional, how do you call the game, like the battleship, right? G4 and so on. So we're doing that, but in 4 dimensions. So we start with our initial population. Again, this is generated at random. And then, we evaluate them. We run for each one of those dots. We run a transport and dispersion model. We evaluate them by comparing the simulated value with the observed values. And then we compute the error. Is it good? Is it bad? Green are the ones that have a small error. Red are the ones that have a big error. And as you can see, there are some dots that, they just disappear. And that is because, they were neither very good or very bad. So we really try to take the extremes of the 2 distributions. We give this to a machine learning classifier. And voila, we get, attribute value rules, which actually what they do, they describe a subregion of the space. And now the next population is generated by new individuals only within the subregion, only within the green region. And just to clarify, this green region is a generalization of the green dots with respect to the red dots. In other words, if you were to overlap them, you will see that all the green dots, they are in this region, and all the red dots are outside. Okay? And once we developed this algorithm, we implemented it, and we applied again, to this problem, and we did all 6 cases, and we tried to do something that we couldn't do before, which is sensitivity on the sensor number. So in other words, we were trying to study whether or not there is a trade-off between the number of sensors and the concentration that they measure. So what the military did, that created all those concentric circles, was it really necessary to have all those hundreds of sensors, or was it enough to have a few, but strategically located? So here we go. It is a big data problem, probably a big simulation problem, and we were able to reduce from 10 million simulation to 10,000 simulations, so it's an order of magnitude of 2. And this is, a little bit the results that we found out. Each one of those symbol represents 30 runs, so, I'm showing you thousands of runs. Each one of those runs, it takes several minutes to run. And we did it, by taking only 3 sensors, 4 sensors, 6 sensors, 9, up to 12, rather than all those hundreds. And we found out that, there is a very strong empirical relationship between the locations of the sensors and the error that we get. So in other words, we don't really have to have so many sensors. It's just enough to have a few strategically located. Very important result. Now, let's apply this entire methodology to something really complicated, to a real problem. Now, the most recent source characterization problem is Fukushima. Now, of course, we know the location here. So the problem is not to know the location. What we don't know is the release rate. How much radioactive material was released over time at the location. And what we do have, we have radioactive measurements all across Japan. We have a few hundreds of those. And our objective is, honestly, to determine the release rate. When was the biggest one? Was it just an explosion and there were like consecutive smaller releases? We don't know that. Here is a map of Japan, as you can see, and you cannot really see it on the screen, but each of the yellow dots represent the prefectures in Japan. Prefectures are a subdivision of the territory, and within each prefecture there are, up to like 30 to 40 stations in each prefecture. And how does the data look like? Well, something like this. So, again, this is the average per prefecture, but we have several hundreds of those time series. So over time, the horizontal axis, it tells us, what is the concentration on the vertical axis. And we can clearly see that there are some spikes. And so now what we want to know is how much material was released at Fukushima to see those kind of signature all across Japan. Okay? So it's a spatiotemporal optimization problem. This is a way, just a graphical illustration of the methodology we developed. We simulate consecutive releases, each one for a fixed time, let's say 1 hour, of a constant Q. This Q is our initial guess. Is what, the Japanese government said that it was, the maximum release. What we want to do is to find out scalars so that, this constant Q can be morphed into those big Qs, okay? And something that, I should mention, we are assuming a linearity in the problem in this case. In other words, if we double the Q, so the strength of the source, the amount of material measured at the receptor will also double. So there is a linear relationship. In this relationship, it is true, mostly true for a short time span. So, on 3 days, 4 days, then it's okay because, we are dealing with agents that are not highly reactive with the atmosphere. But then, at longer time scale, this wouldn't be true because, of course, we have a chemistry in the atmosphere, and those things, they will lead to non-linear relationship. But for this time scale, it's safe enough to assume linearity. So now there is one concept, is that let's say that, we have some pollution in this room. I take, like 1 parcel of air, 1 meter cube of air, and I check, where is this pollution coming from? And let's see that, there is a power plant nearby. Now, all this pollution was not all released at the same time. So a fraction of this pollution probably was released an hour ago, maybe a small percentage 2 hours ago, and another one maybe yesterday, depending on the circulation of the winds and the diffusion of the atmosphere. So in order to calculate how much nuclear material is at a given time, we really have to take into account all the contributive releases over time. So here we have the formula. So the amount of material at location I and at time t is the sum of all different releases. A portion of release 1 times a portion of release 2 and so on. What we are trying to do, we're trying to optimize, these very long vectors in which each releases is weighted by a scalar. This is, our unknowns, so W1, W2, and so on, so that when we compute the amount of material at each location with the observation, we try to minimize the error. So it's an optimization problem in space and time. So this is, this particular vector, it's several hundreds of times point long. It's a constraint optimization. And here is a graphical representation. So here is the different releases that we simulate. I believe there were 68, if I remember correctly. Constant Q, remember they're constant. And if I simulate this, I obtain this in Tokyo. Okay? See the shaded area? How this one is the contribution of all different releases over time? Well, this is what I obtain in Tokyo. Of course, I have, hundreds of those. I have one of those for every location in Japan. And then, for each one of those, I have the red line, what was observed. So right now, what I need to do, I need to make sure that that surface matches the red line all over Japan. It's that vector I showed you before. I optimize it. I use my non-Darwinian optimization. And I come up with this result. Once I got that, I have a set of scalar W. I multiply by my original Q, and I come up with this. So what you see over there, that is my estimate of the amount of nuclear material that was released at Fukushima. This was presented at NSF, and we are within one order of magnitude of different teams throughout the world that use completely different approaches. When you do something like this and you come within one order of magnitude, it means, that you're probably good. And I want to show you that, here, on this constant Q that was our initial guess, the scale goes to up to 1 to the power 8 nanogray per hours. And in here, we're talking about 2 to the power 10 nanogray per hour. So 2 order of magnitude greater of our initial guess. Once I have that, once I have the release rate, I can plug it into my simulation software. And here you have, this is my estimate for the radioactive leak at Fukushima using SkiPath. SkiPath is a transport and dispersion model used both by EPA and by the US military. Okay, good. So now I want to tell you a little bit about the new stuff that I've been doing. The geoinformatics for remote sensing and social media. So remote sensing, so we're talking about data that is remotely collected from satellites and from airplanes, is the de facto standard when we observe the Earth and its environment. It provides high-resolution data. When I mean high-resolution, I mean spatial resolution, spatial, spectral, and radiometric resolution about the Earth. It's crucial during disaster. Every time there is a disaster, everywhere on the Earth, go to CNN, they will show you a satellite image. It's the de facto standard. And it's one of the scientific discipline, at least that I know of, where we truly have an international cooperation. And one of such examples is the International Charter for Space and Disaster. This is an international collaboration of all countries that have space capabilities. And when there was the 2011 Japanese earthquake, the charter was activated on the request of the U.S. government, the Japanese government, and I was requested to help in making some of the images. So this is one, and bear in mind, the turnaround was extremely quick. You know, they need an image, after 1 hour we had to provide it, or something like that. And this means going through terabytes and terabytes of satellite imagery from the past so that, you know, we could see how was the situation before the disaster. And then, you know, the image, as it was coming from the satellite, you know, it had to be georectified, and then, you know, we had to compare them, create, you know, a machine learning classification to identify where the changes occurred. And here in the case of Tugayo, this is one of the examples. This is the previous image about 5-6 days before the earthquake, and this is, you know, the day of the earthquake. There was widespread damage in this area. There was a fire. So, you know, we made a comment to say there is a fire going on there. You cannot see at this resolution, but there are some ships over here that have been washed ashore. This part of land completely got washed out. So it was tremendous damage. We created several of those. And I just wanted to show you, this is the thank you letter from the acting director of USGS with a very nice statement from his Japanese counterpart. So it felt tremendously good, you know, to be able to help during the time of the disaster. However, here we have some challenges. You know, if you watch the videos in Hollywood, they show the satellites, you know, can take any, data about the Earth in any place, but, you know, they didn't take my course, so that is not true. Actually, we're rather limited in what part of the Earth we can see. There are some satellites that can constantly observe the Earth, but those, they are 36,000 kilometers in space. Things like, you know, satellite TV, you know, you have the dish, you point it to the satellite, and then you never have to worry about it. But that's too far to observe the Earth at high resolution. So for this type of problem, we need to use polar satellites. Polar satellites are satellites that go from the North Pole to the South Pole while the Earth spins underneath it. Now, the revisiting time varies. It can be as short as 4 days, as big as 16 days. Okay? Now, of course, we don't have only one satellite in space. We have several of them. So, you know, this revisiting time, it can be shortened as we deal with a constellation. But truth be told, most of the time, we don't really get the data when we really want it. And sometimes, even if we do get the data, we have the problem of the atmosphere. Atmosphere is not transparent. Luckily, otherwise we wouldn't be here. But in the case of, for example, clouds, if we're trying to look at the Earth with the visible and the near infrared, we just won't be able to. We'll see beautiful clouds, but we will not be able to see the ground. So there is a problem here. And how can we solve it? How can we solve those temporal gaps in the data? And here is the idea to use social media. So this is really a data fusion problem in which we have remote sensing data that has a very high spatial resolution, but a low temporal resolution. It has all those gaps. Then we have social media that is sparsely distributed on the surface of the Earth, but has a very high temporal resolution. So here is the hypothesis that, you know, if we join those two, you know, we can get the best of both worlds. And this is one point I always like to make. We're not trying to reinvent the wheel. You know, remote sensing data is used routinely. We're not trying to go to the agency to say, oh, you've done all wrong. You shouldn't use remote sensing. You should use social media. What we're saying is that instead of waiting for the next satellite pass, what we'll do, we'll try to see from the social media if there is enough information in order to analyze a phenomenon that is currently occurring. So here it is, first experiment. We published this year, 2013. Those are the floods for Memphis. And what we have here on this graph on the right is the water height on a river gauge on the river, somewhere right here in the center of the map. And then, you know, we have a high-resolution digital elevation model. And by using this data, particularly we took this data here, this day here and this day here, we were able to estimate what was the level of the water before the flood and during the flood. And then, you know, we took remote sensing data. This is multispectral remote sensing data. We went ahead and we ran a machine learning classification. We identified areas to say, okay, this is a flooded area, so we supervised it. And then we say, classify every pixel. And this is the machine learning classification before the flood and during the flood. Okay? Then what we did, we put those together, so we have this stacked layer approach. There are multiple layers for the remote sensing because each one of them is a different part of the electromagnetic spectrum. visible, near infrared, thermal infrared, and so on. And we have our digital elevation model, and we have the new stuff, the volunteer data, what people just volunteer. And we put it all together. We come up, with flood maps, something that looks like this. Here the diamonds are the news, the triangular photos, and the pink circles are videos. There is a lot of overplotting here. There's actually more data than you see. And our conclusion was that even a modest amount of social media was able to greatly improve our maps. Great, done. Now, does it work for a bigger case? We went ahead and we tried on Sandy. Now, for Sandy, we actually don't have satellite information because, this is a hurricane. The atmosphere will greatly perturb, so for several days it would just cover with cloud. But the Civil Air Patrol, which is the civilian wing of the U.S. Air Force, flew several sorties. It collected thousands of pictures below the cloud so that, we have those beautiful pictures you see here that give us an image of what was going on the day after Sandy. And then, we have YouTube videos for this particular exercise, and we have just, this work has recently been accepted, and we presented it a few months ago at a conference. And now is the first problem. There are so many images. We have thousands of images. How can we find out where there is damage and where there is not? This image was put on the web, and it was crowdsourced. Thousands of people from all over the world went ahead in those images, and they click. Green, no damage. Yellow, medium damage. Red, high damage. This is interpolated data. On each one of those squares, actually you may have from 1 to maybe tens of images, and the color code is the average crowdsourced value for the particular region. Okay, very good. We have this data. It's great. And we thought, well, what can we do? How can we help? FEMA released this map, the one in the top left. This shows us the area that are flooded. Okay? This is a 1 meter resolution, very high resolution, so we know what areas are being flooded. And then, this is the layer that we have. It's the very same image that I showed you before, but instead of using colors and square, I'm using, a bubble graph. So, the larger the bubble, the greater the damage. And then, we have our YouTube videos. As you can see, they're distributed a lot here in Manhattan, here, Coney Island, and right here. And what we were able to do, we were able to color code the FEMA map. Okay? So you see, this is the FEMA map. The FEMA map is flat. It just tells me that the area is flooded. Now what we're doing, we're saying, well, not only is flooded, but some areas are flooded more than others. So it's value-added product. And then we were paid by the Department of Transportation. They asked us to do an assessment on those. And here it is. So we overlay a layer in GIS using the streets. And we were able to assess that the damage to the streets goes well beyond the flooded areas that FEMA gave us. Okay? So all is good. We're able to do this assessment. And now the problem, this was not done automatically. This we've done manually and we've done after the fact. What about if we want to do it in real time? We tried the exercise. We used an artificial neural network. We had, the data for 2 days, 29th and 30th. 29th was, the major day after, the major flood, and 30th, still, major flood, and then it started going down. What we did, we took several layers. So we have, our FEMA map, that's what we're trying to predict. And then we took a whole array of data. We took, social media. We got Twitter data, photos, videos, ground observation from FEMA and from USGS, model data. We ran this in our lab. And then, we used the remote sensing data for Civil Air Patrol. And we trained the network on the 29th, and then, we tested it on the 30th. So fully automatic. And, and this is the image that we got. So, each pixel, actually, in this particular image, we just sampled a few pixels. There are just a little bit too many. And we were able, to, again, color code it, into 3 different categories: high damage, medium damage, and low damage. This was automatically done by a neural network. There was no human intervention in this particular image here. Again, flood in Calgary, one of the most devastating floods that occurred in the region from the 21st to 26th of June 2013. We have remote sensing data before the flood, but not after. Much cloud. However, we have a very high resolution DM from the Canadian government, and then we have hundreds of geolocated tweets, photos, traffic cameras, and news feeds about which streets were closed and which were open. So here is the image from the remote sensing. and with a classification of the flooded area, our digital elevation model. This is the extent of the flood that we have computed by using, the river gauge. And here is just a snapshot. We have hundreds of those, that tells us over time which streets are closed, which are open, tweets, and so on. And here is a temporal estimation of the flood. So this is our estimate of the flood as it occurred in Calgary without using any data other than what was contributed and, those traffic cameras and newsfeed. So we can actually see the event, how, we have the floods, and then, it slowly recedes over time. So this was a very big result, very important result. And we actually, just for fun, we put it on KML into Google Earth. Those are the kind of things that the program manager likes to see because, you can say, oh, that's my office. Okay. Now, while limiting to social media, I know that the title of my talk is about social media. That's because it's catchy. Everybody knows about social media. But then in reality, we've used all sorts of, several types of data. Pictures, videos, microblogging, traffic camera, cell phone. We have used cell phone data. I didn't show it to you, but we did do that. News feeds, and then, power outage. This is actually fun. It's something new. New satellite that is able to detect lights and night. So, we can actually, detect power outage just by looking, how many lights there are. Now, last 5 minutes, I want to talk to you about geolocation information. Because, in order for this to work, we must have geospatial data. Now, when we're talking with those authoritative data, remote sensing data, model data, then, we have very precise geolocation information. It's not a problem. But when we start talking about social media, then here it is a problem. The amount of tweets, for example, that they have precise geolocation information is very small, 5 to 10%. However, the precise geolocation information, it can be derived using some text mining and network mining. Now, when I talk about text mining, I don't talk about just analyzing the text because, very few people say, oh, it's flooded between, 3rd Street and 5th Avenue. That really doesn't happen. Something like this. And this is really, 3 days ago, I went on the web and I did a search for floods. And I picked up, one tweet that I thought it was interesting. See, oh my God, there was a massive thunderstorm and the road outside work was flooded and the sky went all weird and yellow and there was a rainbow. So, it apparently doesn't have much information, but it's very good. I know that something flooded. If I can place these tweets anywhere on the world, it's very useful because I know when it was posted, so I have time information. All I have to do, I have to find location information. How can I do that? Well, I took a look actually at the profile of this person, Alice, and she tells me she's in Leicester. Okay, now I went ahead. There is one Leicester in England, and there are about half a dozen here in the U.S. So, okay, there's still a little bit of uncertainty. She does tell me that we're all mad here, so my guess was this was in England. And actually, I went ahead, and she just bought a Citroën. So, she is indeed in England because there are no Citroëns in the U.S., right? So, you see, I was able, to extract precise or semi-precise information just by looking at the profile. And, on the left, you have my former advisor, my PhD advisor, Menas. And you see, he tells me precisely he's in Marina del Rey, California. How nice of him. So, if I see one of his tweets and he says, oh, it's flooding in front of my house, I know that it's flooding in Marina del Rey. But, not everyone is nice as my sensei. You see this person here on the right, he just say that he's from planet Earth. So, not as helpful. However, remember the tweets are really a network, a part of a network. So we know who is following who and who is retweeting who. So we can actually build a model of a network. And now we can start clustering together. And when I start clustering people together, it's enough that a small percentage of those gets geolocated. And then, I can now, assume that, if I'm talking about, some flooding in Pennsylvania, in central Pennsylvania, and all my friends are from central Pennsylvania, most likely I'm really talking about, something occurring all surrounding to us. Now, I thought, just to conclude, I said, well, let's see if I can find out what NCSU is just by looking Twitter. So I just went to one of the many websites that allows me to geolocate tweets, and I just typed NCSU. You can see there are some dots, throughout the world, but then, there is a very big center right here. You can probably guess I did this in the middle of the night. As my wife would say, very early, I would say very late, because, the sun is coming. But then, perfect, that's where NCSU is. Can it be a little bit more precise? I actually investigated one of the tweets, purely random, and I found out this. this Sean's taxi that is telling me that he's at the NCSU bookstore, which is right there. Now, I don't know very well the campus, but, I'm ready to bet that that is either the bookstore or is very close to it, right? And as I said, I always believe in giving credits where it's due. This is Sean's taxi. If you have any problems after partying, after 5 anti-DUI cab rides with me, you get one for free. And what I wanted to show you is that when he tweeted that, he probably didn't think he would end up right now in this talk. Everyone can contribute greatly, by providing information without intending to. And this is what is really, really great about social media. Conclusion. So what we talk about today, well, hazards pose a constant threat to our society. I want you to remember this. If you can remember one thing out of this talk, please, this is very important. We have an unprecedented amount of geospatial data that is available to us, and we have very sophisticated algorithms that allow us to solve those problems. But, it's not enough. There is not a problem that has been fully solved. There is great possibility to do tremendous amount of research. And this is research that is not only very important from a societal point of view, but then it's also very complex. It's challenging. What about this talk? Well, I told you about, geoinformatics for source characterization of atmospheric contaminant. We also talked about this geoinformatics for the analysis of remote sensing, numerical models, and social media. And as I said, I hope that this will be continued. And I want to thank you again very, very much for allowing me to be here. Thank you very much.
Questions?
Is there any thought to being concerned about the integrity of the types of data that you're pulling in? Is there any idea of how many tweets need to be captured on some type of data before you can say this is good data versus this may be sketchy data?
Yeah, this is a very important question. You asked a question that is really fundamental. How do we know that the data is good, that we can trust it, and so on? So when we created those layer approach, we actually assigned different weights to different layers. So we know, for example, that we trust news feeds more than we trust tweets, for example. And then, we also have, we assign weights according, to the spatial distribution, and we weight that by the population density. So, for example, if I see that there is only one tweet in Lower Manhattan, then, I don't assign a very, very big weight on that because I know that is a very heavily populated area. So a single tweet, it doesn't have much value. But the one single tweet in central Pennsylvania, then, it carries much more information. So one way that we're trying to cope with that is just by looking at the volume. And here we come into that, big data paradox that when we analyze tweets, we usually analyze 1% or maybe 20% of the entire feeds, which is huge, massive amount of data, but it might or might not be a true representative of the entire distribution. So that is a big problem. We also have this problem of big actors, bad actors. So, people that, they purposely tweet wrong information, just to deceive. So this is a beautiful area for research. It's certainly not solved. We're trying, but it's not solved.
More questions? I have one question. We have discussed the data integration problem that seems to be present when you combine different kinds of information. Is it easier? I got a sense from your talk that it's not a difficult problem in this particular case.
Well, no, it's actually very, very hard. Sorry if I gave that impression that it was easy. Integrating data from heterogeneous sources is tremendously difficult. And when we do that, we need to take some assumptions. It's all a matter of how good are the assumptions that we make. And assumptions, they're time-dependent variables. Something that we assume for today may no longer be true for tomorrow and so on. One of my, by the way, I should mention, a lot of the work on the social media is from my PhD student, Emily Schnebly, who will graduate in December. And part of her work is really trying to find out how do we integrate the data and how can we make assumptions. And this really translates in what data do we really need at what time. So if we know that a hurricane is coming, do we really need to collect all this data? Do we need traffic information data 12 hours before a hurricane comes? Probably not. Probably that data we only need it after a landfall is made. So it is a very, very big problem. And I really think, that we're just scraping the surface, and there is not one established way to do it.
And still such impressive results.
Thank you.
Further questions? Thank you so much, Dr. Shapiro.
Thank you very much.